One on my desk. So when you're talking about initial velocity, and this is, I mean, if you're in physics, you'll probably see this again. Sweet. Good luck. Are you, get it? Initial velocity. It's one of those days. There it is. All right, so when we're talking about this whole idea of initial velocity, you have two different types of things. It actually is shown in one of the other work problems of why this stuff works, and it kind of makes sense if you start really thinking about it. When you have an object and then you just drop it, there's no like thrown out stuff to it. It's just gravity. What's this? Well, yeah. Gravity drops the ball. Did I get it? Anyway, so what happens here is that if you have it where you drop it, or if you launch it, or you throw it, okay. Now, if you're launching it, you're giving it an initial velocity. You're sending it upward. So if you throw something, it goes up and comes down, okay. Because again, gravity. If you're throwing something down, you're throwing it with an initial downward velocity. So depending upon how you throw something, or how something is tossed, because if you're just going to throw, obviously when you throw, it still has that parabolic arc to it as it's moving. If you're throwing underhand, it moves up and then comes back down. Okay, so there's still parabolas. Okay, dependent upon velocity and everything. We're not taking into effect any curvatures or spin rates or anything like that. We'll do that when we get to trig, because we can actually do the spin rates of a chip shot in golf. We talk about the initial velocity and all that kind of stuff. So all this is that it talks about the three different variables here. Time is always in seconds. This v sub o is the initial velocity, and then h sub o is the height at which it starts. Okay. So if I'm taking the initial velocity of this ball, dropping it from 6 feet, the function would have been negative 16t squared plus 6. Okay, that's all that means. Bless you. So when you're looking at the volleyball one, a volleyball player on one team spikes the ball over the net, the ball is 10 feet above the court. That's some ups right there. The spike drives the ball downward with initial velocity of negative 55 feet per second. Players on the opposing team must hit the ball back over the net before the ball touches the court. How much time do the opposing players have to hit the spiked ball? Now, that's using this formula here, initial velocity. Okay. So you're using the negative 16 t squared. Now the initial velocity is negative 55. And then what's the initial height? 10. Bless you. So that's a person jumping up 10 feet in the air, spiking the ball, and hitting it with that initial downward velocity. How much time is there before another person, before it hits the ground? So, what's that? That's true. It could have. But let's just say you're super good at math, and you can calculate these things quickly. It would be a lot easier if you were better at volleyball. Sure. Ready? I'll set this to you. Wow. You're cut. All right, so here's what we do. You go to your calculator. y equals. Hear it? Negative 16. And you put the function in. Once you put the function in, we'll look at it graphically. Don't have much time there, don't you think? Okay. It's hard to see here, but you can see that there's a negative time and a positive time. Which time do you think we need to worry about? Positive time. So what I want to do is I want to, remember how yesterday we adjusted our windows to see the heights? Today I'm going to show you guys what can happen if you want to see it closer within that time frame. Okay? Now we know that time is going by seconds. So we know that it's going to happen between 0 and 1 second. Not a lot of reaction time here. So let's change our window. Let's change our x max and min to 0 and 1. 0 for your minimum, 1 for your maximum. Go back to the graph. We don't care about anything else about the graph except for where that crosses the x-axis. Because where it crosses the x-axis is a 0. It's the positive 0. So what we do is we hit second, calculate. Look at that. There's an option for your 0. Now, yesterday we talked about left-hand and right-hand boundaries. Remember that? Same idea here, but this might be a little bit tougher because of the we have to figure out where our curve is. See how right now my y value is negative? That means I'm below the line. I have to bring it back so that it's positive. So I'm working my way back slowly but surely. Good times. Oh, there it is. All right. So I'll do a left-hand boundary, hit enter. Right-hand boundary, and hit enter. Guess, yellow. I have 0.17 seconds to react. Ready? Here you go. Just for the ball. So fast you have to react. At what? All right, here. Thanks. I was really worried about you. That's how you calculate zeros. Your calculator will find these things for you, and they will help you find these things. I think the other problem that was very similar to that was what was it? Jackie Joyner Kersey. Remember that problem? You did that problem last night, right? The shot put. Same basic idea. When you look at this, that's modeling her throw. Her throw is a negative A value, which means it went up and came down. If you think about it, it makes sense. If you're throwing a shot put, you'll throw it up and then it goes back down. Right? Now, why is that? Why is the C value 5.5? That's how high the ball was when she originally threw the ball. Makes sense. So when you start thinking about it, those initial heights, or the C value, tells you where the ball starts. Now, obviously, if you look at that on a graph, the ball isn't going to go behind her and get negative distance. Okay? Bless you. She would not be on the cover of a Wheaties box if that was the case. So what that meant was the ball started at 5.5 feet and she went like that, and we had to figure out how far it went. Well, if you throw this one in your calculator, which I hope you guys did, take a look at that one. Yes, sir. That was bad. Really bad. So let's see here. Negative 0.0241 x squared times 2 for 1. Get it? 2 for 1 deal. You guys missed Sev. I know, he was much funnier. I'm going to go back to my window. I'm going to readjust it because I know that I screwed something up earlier. But do I need to worry about my x minimum? I just keep it at 0 because that's just going to be where it starts from and pushes it outward. I'm going to change my x maximum. I'm going to guess that maybe she could throw the shot put further than 10 feet. I'm hoping. I don't know, so I'm going to say maybe 50. I don't know how far people throw shot puts. Maybe you guys throw shot puts? I don't know. Yeah? How far do you throw your shot put? And we'll see what happens. Oh, obviously not that far. So what I'm going to do is back it up a little bit. We're going to go to... Oh, thank you. There we go. Whee! Wow, what a guess. That's a good throw of a shot put. So how far do we have to figure out what are we going to do? We're going to use 0 here. Now, did any of you guys try to do the axis of symmetry and just double it? That doesn't work. It doesn't work because think about it. Your axis of symmetry, your zeros, you'd have a negative 0 and a positive 0. That positive 0 is going to get, that's going to be the midpoint, but it's going to move it backwards to get your full distance. Here, you're just going to calculate 0. Okay. Calculate your 0. Left bound, let's keep moving. Here it comes. That's for the cannon problem. $46.41. So she can throw the shot put. That's what it sounds like. Shot put. Not the hot put. Shot put. Good times. What's that? That means it's pretty darn close to 0. Guys, if you ever see this value, that the 1e to the negative 12 or something along those lines, that just means it's 0. Okay. The calculator, when it does a lot of that calculate 0 stuff, it does an approximation, and that just means that it's pretty darn close. Not always well the same. So let's talk about some of the other types that are on here real quick. And I'll just let you guys work. Firefighting one, you're calculating your 2 zeros because if you're standing at one spot, one way is here, and then if you have it go the other way, the arc stream can reach another, depending upon how you set the stream up. Yeah, that's all that is. There's 2 of them though. Right, and that's what that means. Yep, that's all it is. So if I go back to the very first page, you have made a rectangular stained glass window that is 2 foot by 4 foot. Wow. Congratulations for staining some glass. That's awesome. It is a... Oh, I've never made stained glass. How do you make stained glass? You just...
You buy the glass.
Yeah, wouldn't it be easier just to, buy a piece of glass that's stained? Or if you stain it, you can pour grape juice on it or something?
That's how I do it.
Yeah, it could be an art project. Very good. So for an art project, you've decided to stain some glass. Yay. You only have 7 square feet of clear glass to create a border of uniform width around said window. All right, border of uniform width. What do you you think that means? Exactly. It's an equal border all the way around. Okay? So we have our stained glass window. We have a stained glass window that's 2 foot by 4 foot. And there's going to be a border of uniform width around it. See how well I can draw that. Yes, I did. Now, if it's border of uniform width, that means that all of this value here is the same as this value here, correct? Well, let's call that value x. Which means this down here is x, here is x, x, x. I just label it so we know where x is. What's my new exterior dimensions? What's my new exterior dimension? What's that? 2x by 4x? No. Go on. No, you were on the right track. I thought you said something first. Yes. Your new exterior dimensions then become this one here, since this is the 2, will be 2 plus 2x, because it's on wider. Here would be 4 plus 2x, because it went wider here. You okay with that? What's happening here is that we're adding what's called uniform width around the corner. So if you're adding a foot up top, you're adding a foot to the bottom, there's 2 feet. Obviously, it's not feet, but in this case, that's what it would look like. Now, if you only have 7 square feet of uniform width, that means we have to figure out what the area is of the border. Well, how do you find the area of a rectangle? Base times height, length times width, okay? Whatever. Now, in that case, then, this is going to be 2 plus 2x, 4 plus 2x. That's the new area of the entire thing. But am I worried about the area of the whole thing? So what do I back out? I back out the original area. What's the area of the original? 8, 2 by 4. What does it have to equal then? 7. It has to equal 7. Uniform width. What happens a lot of times is that you're going to add in x's on tops and bottoms, x's on the left and right, and then you're going to subtract out the middle. Okay? You subtract out the middle, and then that will equal whatever your new area is to be. Okay? So in this case, what we would wind up doing, let me put this on a clean sheet so I have room. We get 2 plus 2x, 4 plus 2x, minus 8 is 7. Foil it out, we get 8 plus 4x plus 8x plus 4x squared minus 8 minus 7 is 0. All I'm doing there is move everything around. Set aside equals 0. Combine our like terms. We get 4x squared. 8's go away. What is that then? Plus 12x and 7. And now you're a factory problem. You're in a factory problem. Or, what are you trying to solve for? What are you solving for? Solving for x, right? Aren't we looking at a graph that does this? What are these values called? Zeros, right? So aren't we just calculating zeros? Would that function in your graph look up there? Uh, 4x squared Thank you. I wasn't sure if it was plus or minus. Plus 12x and then it was minus 7? Thanks. We go back to our graphing calculator now. All right, screwed something up here. Well, I can change my window. Ah, ah, ah. And I have a negative 0 here. Because they're talking about a dimension, aren't they? So all I'm looking to do is figure out what's that value. So what buttons do you press? Yeah. Second, calculate 0. Now, here's what's different. We're checking our left-hand boundary now is going to be below the x-axis. So you're going to be to the left of where it crosses, and your right-hand boundary will be above. I think the other examples that we did, it was flip-flopped. So, enter. Enter. What should your width be around the frame? Half an inch. I'm sorry. Feet, half a foot, 6 inches. Excuse me, I had that. I forgot we were feet. They're asking what should the width of it be? So if we go back to the problem, all the way here, what should the width of the problem be? Well, it should be 0.5 feet, otherwise known as 6 inches. Okay, because your units were in feet. So graphing calculators allow you to be able to figure out real quick without having to factor. Now, could you have factored that? Yeah, it's not that bad. It's what times what was negative 28 you had together to get 12. It would have been 14 and 2. So it wouldn't have been so horrible. That's how that stuff works. The calculators, when I let you use them, you're going to be able to use them to find zeros. Yes, sir. For part of it, for the word problem stuff, a lot of times word problem stuff that I give you guys, you get some pretty crappy numbers. And that's what, yes, I would let you, because that's what I'm hoping that you would do. Not too bad. All right, well, let's talk about cost functions. Athletic wear, number 99. I forgot the page. A store sells, a shoe store sells, it's like Sally sells, she sells, he sells. Right. A shoe store sells about 200 pairs of new basketball shoes each month when it charges $60 per pair. For each $1 price increase, about 2 fewer pairs per month are sold. How much per pair should the store charge to maximize monthly revenue? What is the minimum revenue? I'm sorry, maximum, excuse me. So, a shoe store sells. All right. Well, this, and when you're talking about things like this where you have a sales figure and a cost figure, it's creating a setup like this. You have how many shoes you sell and a price. So you have sale units and price units. Okay. So if I multiply 200 times 60, think about it in terms of foiling, that would tell me how much I would make at $60. Do you agree? Then we have to put in the idea that for every dollar increase, so let me write this out. These are our units. These are our price side. Units can be shoes. The next example talks about stereo or digital cameras. I got one in here about stereo equipment and all that too. CDs. So it says that for each dollar increase in price, I was combining increase in price in price bracket, whatever. So for every dollar increase, how many shoes do you lose? -2. Now, if you think about that, if you did FOIL that out, your A value would be negative, wouldn't it? Your A value would be negative, which means that the function itself would look like this, which means your vertex would be a what? A maximum, wouldn't it? Now, there's a couple of things that you can do here. You could throw it in your calculator, or think about it, what format you have it in. What form is this? Not vertex form, it's intercept form. Intercept form is when you can calculate your zeros. Now, if this is an intercept form, if this is an intercept form, can't I find my two zeros? Take the midpoint, that gives me my vertex. That's what's quick about these. So where are your zeros at? Well, if I want to calculate my zeros here, I'd say 200 minus 2x is 0. 60 plus 1x is 0. Well, I have a 0 then at negative 60, and the other one would be at 100. You okay with that? Now, that means that on my real chintzy graph, if that's negative 60, and that's 100, what's the midpoint of those two? 20, very good. That gives you your midpoint at 20 for your x value. So what's the best price to sell them at? Bless you. Not 20. That was the 20. That's your multiplier. That goes to here. $80. At $80, you will sell the most pair. You'll get your biggest bang for your buck at that point. Okay. Before you guys ever heard the term law of diminishing returns? Law of diminishing returns is that it's basically like this. You can charge so much money for something until no one's going to buy it anymore. Right? So if you're out there and you're selling lemon at a lemonade stand and you're trying to sell lemonade for $2 a cup, you're not going to sell much. But if you sell it for 50 cents, you probably sell a bunch because then at that point, people probably don't have 2 quarters on them, but they probably have $1. Well, they have 20. But I didn't think I even had any money. I was going to say, wow. But they'll have $1 on them, which means they'll probably buy 2. You see what I'm saying? So you learn that. That's why a lot of times you have, like at a ballpark. That's why pops and food and all that stuff for the vendors are like that 50-cent mark. Because I don't even change. That's why they round out. That's why they put it at $2.75 or $2.20, or I shouldn't say nothing's $2.75 at a ballpark. Like the bag of chips is like it's $5.25 because you'll give them 6. Yes, sir. No, it's like 10 1/4. It's at that round point that most people don't have. They're not going to pass quarters through. That's why they do that. Okay. Does that make sense? It's a real fast thing to be able to figure out. So, could you throw it at the calculator and find the maximum? Absolutely. It's quicker to do it by hand because you're using the idea of intercept form to find that midpoint there. Okay. I'm trying to think if there's any other crazy ones in here. You should be able to cruise through. You should be able to cruise through all of these. We'll talk about them on Monday. All right. Yeah. I just wanted to show you the cost one real quick. All right. Yeah. I think there's only like 6 or 7. There's probably like 8 of them I think left. All right. Just be able to cruise through the rest of them. I think I've got enough. I will say one thing. If you want to skip 91, the construction one, where they talk about the parking lot, I'll show you guys. That one's a little bit weird. You can skip that one. I'll explain that one on Monday. But the rest of them are really straightforward. I don't think you're going to have any problems with them. Yes, ma'am.